Okay, in this example, we want to once again apply Stokes' theorem, but this time we're being asked to calculate the integral of the surface integral of curl dotted with the normal vector of the surface. So we're not being asked for the circulation line integral, but we're being asked for the right-hand side of Stokes' theorem. And so let's write down Stokes' theorem one more time before we even finish reading the problem. So Stokes says the following, that the integral over a closed boundary of a surface, the circulation integral that looks like this, is equal to the double integral over the surface of the curl of the vector field dotted with n ds. I'm just going to say one note here. You might recognize this to be a flux integral. So notice that we're taking a vector field, dotting it with n over the surface, and that means we're really calculating flux of the curl. Okay, that was just a note I wanted to add, but we're being asked to find this. And of course, we could do it, just do it, find the curl of this vector field and dot it with n, find the n, and all of these things. Or we could say, well, maybe I can calculate the left side and figure out how I might do that instead. That might be easier. You might think it could be easier because if you take a look at our vector field, doing the curl of this thing might not be fun. So let's see if we can set up our surface, figure out what it looks like, think about the normal to the surface, and let's see if we can actually use the left side of Stokes' theorem to calculate this problem. And I forgot to add here that let's assume that the normal vectors on the surface point outward. All right, so let's get a sense of what we're looking at. What is our boundary? And what does our surface look like? So I'm going to do a sketch of half of a sphere because I know I only want the spherical cap. So notice that our sphere has a radius of square root of 2. So I'm going to draw just a hemisphere with a base that's on the xy plane. And if this is my positive z-axis, I know that this point is root 2. And we actually care about, we just want the surface that's the cap above 1, above z equal 1. So we just want the top of that little hemisphere. And so the boundary of our surface is, in fact, the circle that I drew in green. That's our boundary. That's going to be what we use for the left side of Stokes' theorem. We've also been told that the normals point outward. So we need to figure out, all right, how are we going to orient our curve? So if you imagine that you're walking along the rim of our boundary and your head's pointing towards the normal, pointing out, the region should face to the left. And so I can see that that's going to mean we're going in this direction. So once you have an idea of your orientation, well, in order to calculate the left side of Stokes, we're going to need to parametrize the boundary, which is this circle. So let's find the boundary first, right? We know the boundary is the point where our sphere, x squared plus y squared plus z squared equals 2, intersects the plane z equal to 1. That's going to be our boundary. And so I'm going to plug z equal to 1 into our sphere to get x squared plus y squared equals 1, which is a unit circle at an altitude of z equal 1. All right. And I know now the direction in which it should go, right? Its orientation. So since it's going, if you notice how I oriented it so that it would be compatible with the normals, it's going in the counterclockwise direction, which means that to parametrize this circle, I'm going to need only one parameter, of course, because it's a curve. And I'm going to let the x-coordinate be r cosine t, but r is 1 along that curve. That's fixed. So this will just be cosine of t. The y will be sine of t. And z is 1 because we're at an altitude of 1. And so there's my parametrization. And t really represents my angle, so I'm going to let t go from 0 to 2 pi. Okay, now remember how we evaluate our line integral, right? We have, it's over our closed curve, f dot dr. The way that we evaluate this is we evaluate the vector field along the curve, along the parametrized curve, and that's a dot product with r prime of t dt. And then this will be from t equals a to t equal b. So now that we have r of t, we do need r prime of t, and we also need to evaluate our vector field along the curve. So r prime of t is going to be negative sine t, cosine t, and 0. Vector field evaluated at r of t. Well, our vector field is horribly complicated. So, negative, let's think about this. Our vector field will be negative y. So that's going to be negative sine t. So remember that we're looking up here at r of t. The middle component of our vector field evaluated, well, one good thing is that it has a z minus 1, and since z is 1 in our parametrized curve, all we're going to have for the middle component is x, and that's going to be cosine of t. And then the third component is x squared plus y squared, but we know that x squared plus y squared is just 1. Okay, now we need to find the dot product between these two vectors. So let's do that. Our dot product of f evaluated at our along our curve dotted with r prime of t will be negative sine t times negative sine t is sine squared t. Cosine t times cosine t is cosine squared t. And 0 times 1 is 0. So this will just be a 1, which has become a really nice, easy to manage integral. Our line integral then will be the integral from 0 to 2 pi of 1 dt, which gives us just a 2 pi. So in this example, we used Stokes' theorem to evaluate the surface integral of the curl dotted with our normal vector, or we can also call this the flux of the curl.